In today's lesson, we're going to be looking at Coulomb's law. Coulomb's law describes the force between two charged objects, and it bears a lot of similarity with Newton's law of universal gravitation, which is the force between two masses. So first off, we're going to be looking at, I'm going to briefly describe the four major forces that physics looks at, and then we're going to dive into Coulomb's law. First off, in physics, we generally view forces as coming in four major types. And these forces are the strong nuclear force, the electromagnetic force, which is what we're going to be starting to study, the weak nuclear force, and the gravitational force. These are basically in decreasing order of strength. The strong nuclear force is the force responsible for keeping the nucleus of the atom together. Without that strong nuclear force, all the positive charges that exist in the nucleus of the atom would just fly apart and our atoms would fall apart. Okay, the electromagnetic force is that repulsive or attractive force between positive charges and negative charges. The weak nuclear force is the one responsible for responsible for radioactive decay. And gravitational force is primarily that force of gravity that we feel. Frequently, people confuse the gravitational force as being really, really strong. But the only reason we see it as strong, or we feel its presence, is because the size of the Earth is just so incredibly massive, okay? It's on the order of 6 times 10 to the 24 kilograms, which is an awful lot of zeros, okay? It's more than a mole of kilograms. Coulomb's law basically describes the force between two charged objects, okay? And you can think of the force between two charged objects as being proportional to the product of the charges and inversely proportional to the square, the distance between the objects. Mathematically, we would write it as we see on the bottom, okay? That little fish symbol is actually the math symbol for proportional to. It simply means that if I change the right side of this equation, the left side will change by a similar amount. Okay, so if I double Q1, the electric force will also double. If I double the distance r, then my electric force decreases by a factor of 4 because r is squared. That's what that means. I can change this to an equality statement by simply putting a constant in. Okay, and if this statement, okay, seems familiar, it's because it is the same statement we pretty much made for Newton's law of universal gravitation. The only difference being, instead of charged objects, we used masses. Okay, so this is Coulomb's law. Okay, Coulomb's law basically says that the electric force is equal to this constant K. K is Coulomb's constant, times the charges Q1 times Q2, all over the distance r squared. Okay, r is the distance between the center of the objects, just like we talked about the distance between the center of masses for Newton's law of universal gravitation. Okay, so K is this constant, and it has a value of 8.99 times 10 to the 9th newtons times meter squared over Coulomb squared. Okay, I will frequently simplify this to 9 times 10 to the 9th, or I'll say it as 9e9. Okay, when I say it fast, it sounds kind of lyrical. Okay, it's 9e9. So that's why I kind of use that number, and it's incredibly close to that number without sacrificing too much in terms of significant digits and rounding. Before we continue, I do want to go into a little bit of metric prefix review, because these metric prefixes are going to be used a lot, and I don't want people confusing or not misremembering them. First off, micro is that funny little U with a tail in the front, and U is going to equal 10 to the minus 6. That's micro. So when I say 2.5 microcoulombs, all I need to do on my calculator especially is replace that micro with its 10 to the power prefix. So micro becomes 2.5 times 10 to the minus 6 coulombs. Similarly, we'll see a letter N. Okay, it's not a Greek letter, it just really is N. Okay, and that's nano, and that's going to represent 10 to the minus 9. Okay, so 6.4 nanocoulombs becomes 6.4 times 10 to the minus 9 coulombs. So for example, I have a minus 3.8 nanocoulomb charge and a plus 2.5 microcoulomb charge, and we separate them by 81 micrometers. Okay, find the magnitude of the electric force. Well, this is a prime use of the Coulomb's law, so I have all the numbers that I need, and I can plug it into my calculator using the metric prefixes shown below. Okay, notice that I did not use a minus sign or a plus sign in my numbers below. Okay, the 3.8 times 10 to the minus 19. Okay, that's still going to be 3.8 times 10 to the minus 9. 3.8 times 10 to the minus 9. Okay, so here's the, oh, that's ugly. Okay, so here's the 10 to the minus 9th. Okay, 3.8 times 10 to the minus 9, and there's no sign. And the reason I ignore the signs in this case is because force is a vector. Okay, as a vector, the magnitude of all your vectors should be positive. So it doesn't matter what I use, as long as my answer comes out positive. The minus sign we'll talk about a little bit later, but the minus sign, again, only indicates direction. If it's one-dimensional, we're usually talking left and right. And if it's two directions, it's plus x minus x, plus y minus y. You know, or if you get more complicated, there's a z-axis for the third dimension. Okay, so to make your life easier, just use all positive numbers for this unit. Okay, that's why on the previous slide, okay, I have absolute value bars on Q1 and Q2. Okay, simply just ignore the signs and use them here. When you're trying to figure out direction, that's when the signs need to come back. Okay, and that's where this slide is about. Okay, because to determine the direction, we're not going to be looking so much as left and right or up and down so much. Instead, we're going to be wondering, are the two forces attractive or repulsive? The reason we're not going to be looking so much at left and right is because there is one left force and one right force on all of these diagrams. The reason for that is because these forces, two forces, represent a Newton's third law pair. Okay, the force of A on B, here's A, and here's B. Okay, the force of A on B, which is this force here, okay, is going to equal the force of B on A, which is this force here. Just equal but opposite. So they both have a left and a right. It's only when I want to know about the specific force on A or B, instead of the force between both of them, okay, that I would focus on the left or right and make one either positive or negative. Okay, and it's important to remember that like charges repel each other, so two plus signs will repel each other. Okay, they want to move away from each other. Two minus signs, similarly, they want to move away from each other. Okay, when the signs are of opposite, okay, I have a plus charged object and a minus charged object. These two objects will attract each other. Okay, they want to move towards each other. Okay, so in terms of the direction of electric force, okay, we need to examine both charges, okay, and describe our forces as going to be either attractive or repulsive if I'm looking for the force between two objects. I'm not talking about one specific object. When I get down to finding the force on a specific object, either the left charge or the right charge, that's when we can start looking at, oh, well, is my force, direction of my force either to the right, in which case it's positive, or to my left, in which case it'll be negative. Okay, so just as a bit of example or a bit of practice, blue charges are positive, red charges, red dots are negative, and I want you to figure out the direction of the force between these. Okay, I have four different situations: the one on the left, top, bottom, and the one on the right. Okay, so if you figured it out, okay, blue and red are opposite charged, so the force on them is going to be attractive. Okay, they want to move towards each other. Equal but opposite, remember. Red and red is going to be repulsive, so they want to move away from each other. Okay, equal but opposite again, just away from each other. Same with the two blue charges, okay? Same charge, equal but opposite, and they move away, okay? The last situation is a little bit trickier because it's kind of like, it's not up or down or left or right. It's at this diagonal, but there's nothing different about that, okay? They're opposite sign charges, so if I think about it, there's a straight line that goes between them, and the force is in the direction of that line, okay? So the red charge is attracted to the blue charge in the direction of that line, and the blue charge is attracted to the red one similarly in the direction of that line. Okay, so hopefully you were able to get those right and it wasn't too much of a problem. Okay, this last slide is basically kind of a summary of the differences and similarities between gravitational force and electric force. First off, they're both forces, okay? So they're both newtons and they're both going to be vectors, okay? They're both inversely proportional to the square of the distance, so as I get farther away, it gets weaker faster. Okay, the force is always going to be measured from the center of the objects, center of the masses, center of the charges. And the forces are going to be proportional to the product of the two masses or product of the two charges. Okay, this is a physical quantity. This is where they're different. Okay, the last two are differences. Okay, electric force is very strong because the constant that we use, this 9 times 10 to the 9th, that's plus 9. Okay, as a magnitude, which is the exponent of the power 10. On the other side, I have the gravitational constant, okay, 6.67 times 10 to the minus 11. Between minus 11 and plus 9, there are 20 orders of magnitude. So you could claim that the electric force is not 20 times stronger, but 10 to the 20 times stronger than the gravitational force. Okay, and the last point I want to make out is the electric force can be both attractive or repulsive. The two charges can actually repel each other. The gravitational force, on the other hand, is only attractive. Okay, thank you very much.